Greetings! Welcome to Electronics 2. This is lecture number 22 and I am Razavi. Today we will continue our studies of the frequency response of various amplifiers and delve into a little more the frequency response of the common source stage and common emitter stage, which we studied last time, and then continue with the study of the frequency response of the common base / common gate stage and see how that behaves and how we can formulate its behavior. Okay, but before we go there, let's just look at what we covered last time. We said that the common source stage and the common emitter stage really can be treated in the same fashion as far as the analysis of the frequency response is concerned. The only difference was R pi of the bipolar transistor, which we decided to merge with this source impedance, source resistance, using a Thevenin equivalent. And we saw that then the two circuit topologies are similar, so whatever equation we derive for one is applicable to the other one as well. So we proceeded with the analysis of the common source stage. We identified 4 capacitors for the MOSFET, but one of them goes from the source to bulk, so that's gone, and we have only 3 capacitors. So we wrote 2 KCLs, we solved them and so on, and this is the resulting transfer function that we have. Okay, so it's a pretty big transfer function. It is of second order. You can see that in the denominator we have s squared and s. We do not have s cubed. And then the numerator we have 1, 0, because if we equate this to 0, we get the 0 equal to Gm over CGD. Now we said that the 0 usually appears at very high frequencies, so it doesn't really bother us. We don't worry about it, so don't worry about that. But of course it has 2 poles, and the 2 poles ultimately limit the bandwidth of the circuit. So those are definitely of interest to us. Okay, so now if we do have numerical values for these capacitances and resistances and the transistor parameters and so on, sure, we can plug them in here. We have a quadratic equation. We can find the 2-pole frequencies, right? Not a big deal. But that's not what we are really looking for. We want to have some intuitive understanding of the limitations of the circuit, because we may not even have picked the numbers yet, right? We haven't selected how much this resistor has to be, or what this is from the previous stage, or how wide this transistor should be, how much current it should carry, all these things. So we would like to see the trade-offs first in terms of fundamental equations before we go and select values. Okay, all right. So in general, of course, solving this quadratic doesn't help us much. We end up with an equation this big, and what do we do with it, right? So instead, we resort to an approximation called the dominant pole approximation. And this approximation is good in many cases, as I said, maybe 80% of cases. So it is a powerful technique that allows us to greatly simplify this and have a better understanding of its consequences. All right, so we're going to talk about the dominant pole approximation and see what that means. So dominant pole approximation. All right, so let's suppose that we have a second order system as shown here, and we call the denominator just something like d of s. So the denominator is d of s, and it's a second order system, so it has 2 poles. So we're going to write the poles in the following form. We'll write s over omega p1 plus 1 times s over omega p2 plus 1. We choose this form rather than write s plus omega p1 times s plus omega p2, because this gives us an s squared, an s, and a 1. So the constant value is a 1. right? Everything is normalized, so that gives us a 1. And that's very nice, as you will see shortly. So we always divide everything so that in the denominator we have s squared, s, and 1. Okay, so if that's the case, let's just expand this, right? We're going to write this as s squared over omega p1 omega p2 plus the sum of the inverse of the poles, so 1 over omega p1 plus 1 omega p2 times s plus 1. All right, so that is the equivalent quadratic equation. All right, now the meaning of the dominant pole approximation is that we assume one of the poles has a much smaller magnitude than the other one. The hope is that both poles are in the left half plane, so they don't have a positive value. Really, they have a negative value. But if you look at the absolute value of the poles, one of them is much closer to the origin than the other one. So for example, one pole is at 1 megahertz, the other pole is at 10 megahertz. So it's 10 times farther, so we can consider the first pole the dominant pole. Okay, so then let's write that assumption. We say that omega p1 is much less than omega p2. And I would like to see what simplification we can get from here. Okay, so because omega p1 is much less than omega p2, we see that 1 over omega p1 becomes much greater than 1 over omega p2, which means this coefficient of s becomes approximately equal to 1 over omega p1. So I'm going to write that up here because it's a critical result. So we see that the coefficient of s is approximately equal to 1 over omega p1. So let's write that. The coefficient of s is approximately equal to 1 over omega p1. So voila, that is our pole frequency, right? Inverse of the pole frequency. So if I want to find the first pole, the dominant pole of the system quickly, I can just go look at the coefficient of s, this whole thing, and invert it and call that the first pole, omega p1, the dominant pole. All right? Okay, so that means that for the circuit at hand, this circuit, the dominant pole is given by the inverse of the coefficient of s. So the inverse of this whole thing. So that would be equal to 1 over 1 plus GMRD CGD plus CGS times RG plus CGD plus CDB times RD, right? All of this stuff here. Okay, so two questions come to your mind right now. Can I always make the dominant pole approximation? No, not necessarily. It just depends on the values, right? So what we do is we make this approximation, this assumption. We proceed. We take this guy, find this value, find omega p1. Then we can also find omega p2, as I will show you shortly. And then we compare and see if the assumption is true. If the assumption is valid for a numerical situation, then great, this is good. If not, then we have to go back and solve this equation exactly. Question number 2 is, how do I find omega p2? Well, that's easy enough. We go back here and again observe that the coefficient of s squared is equal to 1 divided by omega p1 omega p2. So because I already found omega p1, I can readily find omega p2. So omega p2 will be equal to, so first we have to invert the coefficient of s, this whole thing, right? First we have to invert that. that would be that would be omega p2, omega p1. And then we have to divide it by omega p1, right? So we say omega p1, omega p2 is equal to this entire expression. So remember, this consists of the cross product of the capacitors, the three capacitors, all added to each other, and then multiplied by the two resistors that we have at the gate and at the drain. So that would be the inverse of all of this. So that would be 1 over CGD, CGS plus CGD, CDB plus CGS, CDB times RG, RD, right? So the product of the two poles is approximately equal to the inverse of the coefficient of S squared. All right. Okay, I'm looking for omega p2. I already have omega p1, right? Omega p1 is 1 over this. So omega p2 would be this divided by omega p1, which means this multiplied by this, right? So omega p2 will be all of this stuff here times all of that stuff here, right? So because I don't want to write out everything, I'll just put some arrows so that you know what to do. So this whole thing goes over here, and then this whole thing goes over here. Well, some very large expression, right? But the point is that we could find omega p2 if we wanted to, right? Okay, so the dominant pole approximation allows us to also see some interesting trade-offs, some trends in the circuit. Because we have found the dominant pole, which is the most critical pole in terms of bandwidth, as a function of basic circuit parameters. So I can see what I can do with different circuit parameters and then see what happens to the first pole. Okay, so last time we applied Miller's theorem to the circuit, and we found an input pole. So remember, so from Miller's theorem, we found an input pole because I took this capacitor, multiplied it by 1 minus AV, which is 1 plus GMRD, and then added that to this one, and then multiplied that by this one, and then I inverted it, right? That was the input pole. So omega Pn is equal to 1 plus GMRD times CGD plus CGS times RG. So this is of course an approximation because we have used Miller's approximation. Miller's approximation is that we are using the low frequency gain from here to here for the multiplication effect on this capacitor, right? That's not true because at the frequency of interest, the gain from here to here is no longer GMRD, right? These capacitances are affecting the circuit, so the gain is lower than GMRD, but that's the assumption. Okay, so you see that we use Miller's approximation to arrive at this expression. We use the dominant pole approximation to arrive at this expression for omega p1. And they are somewhat similar, right? So you can see that most of the components are there. So we have the Miller effect of CGD plus CGS, right? Multiplied by RG, as we would expect when we are trying to associate a pole to one node. Now here we have that. We have 1 plus GMRD times CGD plus CGS times RG. But then we have one more time constant added to this time constant. And that's RD times CGD plus CDB, right? So we don't have much intuition to talk about this, right? You can say, well, our CDB IC, CDB and RD form a time constant at the output. Now this one, well, not quite. It's not really from here to ground, right? So it's different. But approximately speaking, that's what we have. All right, so these two results are comparable. Okay, all right, a few other important insights that we need regarding the frequency response of the stage. So a few points. All right, number one, anytime we derive a transfer function for a circuit, it is a good idea to try some extreme cases and see if the result makes sense. For example, let's assume S is 0. If S is 0, it means that we are working at very, very low frequencies. So if S is 0, what do we get here? We see that this goes away, we have minus GMRD, and then the denominator, we have 0 here, 0 here, and 1. So that makes perfect sense. At low frequencies, these capacitors are open, no current flows through them, and the voltage gain from here to here is just minus GMRD if we neglect channel length modulation. This RG does not have a role in the voltage gain of the common source amplifier, because at low frequencies, when we look at the gate, it's open, right? There's no current flowing through RG. So RG plays no role. Okay, only at low frequencies. So we say if S is 0, then V out over V in is equal to minus GMRD, as expected. Okay, so at least that part of the equation checks out, right? It shows that we haven't made a mistake, at least for low frequencies. Okay, now sometimes it's also good to let S go to infinity and see what happens at very, very high frequencies. In this case, if S goes to infinity, this goes to 0. Why? Well, because at very high frequencies, if we generate a signal here, the signal will be shorted to ground by this capacitor and also by this capacitor, right? So at very, very, very high frequencies, we get no signal at the output. It's all attenuated completely. So yes, V out over V in at infinite S will be 0. So that's also good to know. Of course, nothing surprising really. So if S goes to infinity, then V out over V in goes to 0. Right? This is what you would call a low pass filter, because low frequencies can go through it, high frequencies cannot go through it. Okay, all right. Now, regarding the dominant pole approximation, what we see is that it allows us to quickly reduce a quadratic equation to something simple, right? We just take the coefficient of S and invert it, and that gives us a dominant pole. So it becomes very handy in many different applications, especially in more advanced courses if you take, for example, op-amp design courses and so on. All right. Let me just take a look here and see where we are. Okay, so the next point that I wanted to raise is we have 3 capacitors in the circuit, but we have only a second order system. Why? Why is that? So we have 3 caps, but a second order response. Why? Now, in basic circuit theory, you might have had this concept that if a circuit contains n capacitors and none of them are in series or parallel, then the final transfer function should have an nth order, right? And more generally, if you have n storage devices, some capacitors, some inductors, the total number is n, and again, no parallel or series combinations between the capacitors or between the inductors, then the order of system should be n. And the way we're thinking about this is that for every capacitor and every inductor, we have a differential or integral relationship between the voltage and the current. So when we have n of these in the circuit and we simplify everything, we write out the whole differential equation, it should be an nth order differential equation. So that would indicate that it should be an nth order transfer function. Okay? All right. Well, that's not entirely true. So let me write this here. If we have n caps, again, no series or parallel combinations, right? Because those obviously will simplify, so we'll simplify those. If you have n caps, you would expect an nth order differential equation for the time domain behavior of the circuit, right? So don't worry about transfer function yet. You have this big RC circuit, lots of R's and C's and maybe dependent sources and so on. We write the differential equation for V out as a function of time. And what you would see is something like this, right? So V out, let's erase this. So we have an nth order differential equation, which we will write as dn V out dtn plus dn minus 1 V out over dtn minus 1 all the way to V out equals maybe 0, maybe some number. It doesn't matter here, okay? That's the nth order differential equation. Okay, so yes, that's true. If you have n capacitors, you will get an nth order differential equation. But to solve this differential equation, if let's say you have all the numbers, right? Of course, there will be some coefficients here called alpha 1, alpha 2, alpha n, right? So going from n to 0, alpha n plus 1. So that is a more general equation, some constant values here. So if you have an nth order differential equation, okay, very simple linear differential equation, and we want to solve it, we know how to solve it, right? Actually, we write a characteristic equation, which is of nth order, and solve it and find the roots, etc. But ultimately, when you're trying to find the numerical values for V out as a function of time, what you also need are n independent initial conditions for V out, right? An nth order differential equation can be solved only if you have n initial conditions for it, and those have to be independent. So this needs n independent initial conditions. If we do not have n independent initial conditions, we will not be able to actually solve the final equation, right? There will be one unknown in there and we don't know what to do with it. One of the constants will not be known. Okay, so the question is, does this circuit allow 3 independent initial conditions on the capacitors? And we see that no, it does not. So let's say, again, the time domain, let's assume that I have 1 volt across this and 2 volts across this. Then can this third one have its own initial condition? No, because we have to satisfy KVL. This voltage plus this voltage is equal to this voltage. So if I know these two voltages at time 0, then this voltage is given, right? We say these capacitors form a loop. Because they form a loop, one of the initial conditions is removed. We have only 2 independent initial conditions, right? If I have this, I have this, and so on. So it is because of that that this system reduces to a second order system and is not a third order system. Okay? All right, so that's just a point of curiosity. If you're not interested, don't worry about it. But oftentimes that is also helpful in predicting what order the system will have even before we write out everything. All right, let's move on and go over some examples so that we are more comfortable with these equations. Okay, so here's one example. Let's see. Okay, so we have a simple common source stage, just the way we analyzed it. And it has this resistor. Again, as I said last time, this is not something that we add deliberately to the circuit. It represents the output resistance of the previous circuit, whatever is connected before this one. Okay, so V in is here. And then V out is here. We have RD. And what we do in the circuit is what happens if W goes to 2W, but ID is constant. Okay, so I have a MOSFET. The MOSFET has a width and a length that are under my control. So I designed the circuit with some W, let's say 5 microns, and now I decided to change it to 10 microns. So the width is 10 microns now, but I kept the bias current constant. So the bias current is still the same as before. Let's say it was 1 milliamp, it is still 1 milliamp. And when we say what happens, we mean what happens to the frequency response of the circuit. All right? Okay. So, well, we have these caps. And what we know is that all transistor caps are doubled. Okay? So that's exact. When we double the width of the transistor, all of the intrinsic capacitances of the device also doubled. Why? You can think of it like this, that if let's draw a MOSFET looking from the top. So this is the gate and source and drain, right? And it has certain W. Now, when I make this 2W, it is equivalent to something like this. We take this MOSFET, we copy it, each one having a width of W, and we put them in parallel. So we short these two, we short these two, we short these two, right? That is equivalent to having a width of 2W. So this is equivalent to having a width of 2W, right? So again, in terms of the, so it is like putting two transistors in parallel. So when you put two transistors in parallel, so think of it this way, right? You have one transistor like this, and then you put another one like this, right, in parallel. So now I can see that there are two CGSs, there are two CGDs, there are two C drain bulks, everything, all of the capacitance is double. Okay, so the capacitance of the circuit doubled. Anything else? Well, the transconductance of the transistor goes up a little bit, right? So we know that GM, one of the equations that we have for GM is this, 2 mu n C ox W over L ID. We kept ID constant, but we increased W by a factor of 2, so GM goes up by a factor of square root of 2. So that goes to square root of 2 GM. Okay, let's go and look at the dominant pole equation that we had from the previous page. Right, so omega p1 was given by something like this. We had the Miller effect of CGD, we added to that CGS, we multiplied this by the source resistance RG, and then we add another time constant from this output node or output network. So that was CGD plus CDB times RD. Okay. And what we're doing is we are multiplying all of these by a factor of 2. So let's go and pick this color. So there's a factor of 2 now here. There's a factor of 2 here. There's a factor of 2 here. And there's a factor of 2 here. And the GM is also multiplied by square root of 2. So what happens to omega p1? Well, if you don't worry about this for a moment, we see that every term here is doubled. So omega p1 goes down by at least a factor of 2. So omega p1 drops by at least a factor of 2. Right? It goes down a little more because this also has gone up in the denominator. So omega p1 goes down by a little more than a factor of 2. Okay? So that's not particularly good, right? We reduce the bandwidth. Okay. What else happens when we do this? Well, because GM went up, the voltage gain of the circuit goes up, right? The voltage gain used to be minus GMRD. Now it's minus square root of 2 GMRD. So what we see is that the low frequency gain, which we usually call AV goes up to square root of 2 times AV. So let's try to sketch the two cases as far as the frequency response is concerned and just visualize it, right? For now, we're just looking at the first pole using a dominant pole approximation, just so that we have a feel for what's going on, right? It doesn't mean that dominant pole approximation is valid all the time, but it's a good example. All right, so here's what we have. Let me start with blue. Well, let me start with black for the axes. Okay, so I'm plotting the magnitude of the transfer function. The transfer function is V out over V in as a function of omega. Right now, I'm just looking at the first pole, so we just focus there. The first pole is here, omega p1. And originally what we have is something like this. It goes here. And then, of course, there's omega p2, etc., right? Okay. And what we know is that this gain here is GMRD. Now, we go to, I use this orange color to show what happens after I doubled the width of the transistor. So, we see that the low frequency gain goes up by square root of 2. So it goes up here. So this value is now square root of 2 times the GMRD. So this goes on. But then what happened to the pole frequency? The pole frequency went down by at least a factor of 2. So now it's, let's say this is a linear axis, although it's really a log axis, but anyway. So it goes down to 0.5 omega p1 or less. So this goes over here. And now this goes like this, right? And then again it reaches the second pole, etc. So what we see is that we have some more low frequency gain, 40%, 41% more low frequency gain at the cost of reducing the bandwidth by a factor of 2 or more, right? So that's the penalty that we paid. We increased the gain by 40%, but we divided the bandwidth by a factor of 2 or even more than a factor of 2. All right, okay, so that's a good example of how we have to play with bandwidth and gain of the circuit. And we will see that there is always a trade-off between how much gain we can get and how much bandwidth we can get. So in fact, that brings me to the next example, which elucidates this point even better. So let's look at that. Okay, suppose we have a common emitter stage, and this time we will simplify it as much as possible. We say, don't worry about the transistor capacitances. Okay, let's say they're negligible. So we have an input here. We have a collector resistor here. The transistor is biased properly, everything is good. It's amplifying. And the only thing is that this amplifier has to drive some load capacitance. So here's a load capacitance that we have to drive. We call it CL. Where does this come from? Well, a lot of times you have an amplifier here, you have to drive a wire. So there's an amplifier in this microphone, has to drive this wire. This wire has capacitance. Or you have something on a printed circuit board, the trace on the printed circuit board has capacitance. So it's, this is everywhere. Anytime an amplifier has to drive something, that something has capacitance. So we simplify the situation to only one capacitor, the load capacitor, and we want to study certain things. Okay, so if RC goes to RC over 2, what happens? All right, so assume that transistor is biased properly and everything. The collector current, the bias current is constant. So IC constant. And all we do is we reduce the load resistor by a factor of 2. We would like to plot the frequency response and see. All right, so here's how it goes. This is very simple. There's only one pole. So again, the magnitude of V out over V in as a function of frequency. So initially, when we are here, we have a certain voltage gain, GMRC. This is absolute magnitude, so there's no negative here. And this goes on until we reach the first pole. So the only pole. So that pole frequency is given by, if you just use by inspection, this capacitance times this resistance. So it's 1 over RC CL. Okay? All right, and then past that point, we go down at 20 dB per decade. So here's how it goes. All right, so that is the original design. Now I came along and I reduced the collector resistance by a factor of 2. So that happens. Well, we switch our color. Now we are at GMRC over 2. So the gain is now lower, right? The low frequency gain is lower, but the bandwidth is doubled because RC is halved, right? So now we go over here and we actually go like this. So this would be 2 over RC CL because RC has changed to RC over 2. When we have RC over 2 and CL, the pole frequency is given by 2 over RCCL. So you see what happened? I reduced the gain by a factor of 2. I increased the bandwidth by a factor of 2. So we say that we are trading gain for bandwidth, right? And in this case, they're just proportional to each other. So we say that, in fact, we sometimes quantify this and say the gain bandwidth product, okay, this is called the gain bandwidth product, is constant in this circuit because the gain in the original case was GMRC and the bandwidth was 1 over RCCL. Now you're welcome to add 2 pi here if you want, it's okay, it doesn't matter that much. So this is just GM over CL. So interestingly, it is independent of RC. And that's why when we decrease the resistor by a factor of 2, the bandwidth went up by a factor of 2, such that the product is still the same as before. Okay? So in many circuits, in all circuits actually, we are dealing with a trade-off between the gain of the circuit and the bandwidth of the circuit. In this case, it's very simple. The gain bandwidth product is just constant. So there's not much we can do if we just play with RC. All right? Okay. So, but there's one more thing that we can do. So let's consider this scenario number 1. Now let's go to scenario number 2. So RC goes to RC over 2. But I will also double the collector current, meaning the bias current, right? I double the bias current. Now what happens? Okay, so for this scenario, I will use a different color on this plot to show you. All right, RC. What happens when IC goes to 2IC? We see that GM goes to 2GM. GM of a bipolar device is given by IC over VT. So if IC doubles, GM doubles. So the voltage gain at low frequencies is still GM-RC. RC over 2 times 2GM, right? So we are back here. What happens to the bandwidth? Well, because the load resistance has gone down by a factor of 2, the bandwidth has gone up by a factor of 2. So now we will be on this plot up to here, and then we go down. So what happened? We managed to increase the gain bandwidth product by a factor of 2. So you see in this case, gain times bandwidth is equal to GM-RC times 2 over RCCL, and that's 2 GM over CL. Right? So we see that in the first case, we were only playing with the resistor, and that did not change the gain bandwidth product because it's independent of the load resistor. But what we see here is that it is a function of GM, and the GM is a function of the bias current. So if I play with the bias current, I can change the gain bandwidth product. So yes, I managed to increase the gain bandwidth product by a factor of 2 if I double the bias current of the transistor. So did I gain something for nothing? Is it a free result? No, it's not free. I am doubling the power consumption of the circuit, right? So the power consumption of the circuit is given by the supply voltage, the battery voltage, times the current that we draw from it, right? So now it's VCC times 2IC. So we see that the power consumption is doubled. So yes, we managed to improve the gain bandwidth product, but what we paid is the power consumption of the circuit. All right, so these are fundamental concepts that we need when we are designing circuits and pushing for bandwidth and speed. Now we see that we have a trade-off between the gain, the bandwidth, and the power consumption, right? So now we have 3 parameters. So we have to juggle all these 3 all of the time. All right, very good. Let's move on. So we don't have much time for the common gate frequency response analysis this time, so I will have to defer that to next time. But while we are on these examples, I wanted to show you that sometimes we have to simplify things so that we gain additional insight, right? If I wanted to go with the original circuit with all the capacitors in it, it would be harder to see this very simple relationship that we have among 3 parameters, right? So a good engineer should know when to neglect and when not to neglect various effects in a circuit, right? So here we neglected other capacitances and just focused on this. So we say if it happens that this pole is dominant, if this pole is determining the bandwidth of the circuit and the other poles in here are not that important, they're far away, then we have to focus on the gain, the bandwidth, and the power consumption. And it is these three that will tell us what kind of performance envelope we have. All right, this concludes the lecture this time. I will see you next time.